Hello dear students, in this class let us look into the moment of inertia of a circular disk. So in a disk we have continuous mass distribution from the center up to the radius r. Instead of a ring we have mass distribution inside this radius region as well. So to calculate the moment of inertia we will look into two different cases here. First we will calculate the moment of inertia about an axis passing through the center of this disk and perpendicular to the plane. You may imagine that axis like this. This is an axis corresponds to that axis, and we are rotating this disk like this. In the second case, we will look into the moment of inertia of the disk about an axis passing through the diameter of the disk. So to calculate the moment of inertia about this axis as indicated, we will use a special trick. Just like we calculated the moment of inertia of a rod by dividing the rod into small elements of length dx, in the case of a disk, we will divide this whole disk into small annular rings. So the disk is composed of small rings of different radius. So you can see like this. From center r, center 0 up to radius r, you have small rings of different radius and same thickness, and that is how this disk is composed of. This disk is made up. Now let us look into each of these annular rings. First we define the mass per unit area of the disk. Which is equal to mass by area. We define this term as sigma, which is equal to m divided by the area of the disk, which is pi r square. And now when we look into one particular annular ring, it might be at a distance of small r from the center or small x from the center. These x values may depend on the choice of the ring, and this small disk, this small annular ring has a thickness of dx. Now you already know about the perimeter of a ring, right? If you consider a small annular ring like this, we are looking to find the area of this annular ring. To calculate that, we use a small approximation, which is quite common in physics to calculate the area of annular ring. We calculate the perimeter of this ring. If x is the radius, then approximately the perimeter is 2 pi x. And if dx is the thickness of this ring, area is given by the perimeter multiplied by the thickness, a kind of length into breadth effect. 2 pi x is the total perimeter and dx is the thickness of the annular ring. So 2 pi x is the perimeter and 2 pi x dx will be the area of the annular ring. Now the whole disk is comprised of a lot of annular rings like this that is situated as various x values. The thickness of all of them are same, which is dx. So let us write the area of the ring is equal to 2 pi x, which is the perimeter, multiplied by the thickness, which is dx. And hence the mass of each of the ring can be written as the area multiplied by sigma, because sigma is the mass per unit area, right? So multiply area with sigma to get the total mass of each of these rings. So that will be the mass of the considered ring at a distance of x from the axis. Now what will be the moment of inertia of that ring? Since it is a ring, you may write 2 pi x dx into sigma is the mass of the ring multiplied by radius square, x square. This is the moment of inertia of that ring. Now this is equal to 2 pi sigma x cube into dx. We have already calculated the moment of inertia of a ring like mr square. This is m and this is radius r. Here we have chosen x as the radius of the annular ring. Now we have obtained the moment of inertia of a single ring inside the disk. The whole disk is made up of a lot of concentric rings from 0 up to capital R. To calculate the total moment of inertia, we will have to integrate from 0 up to capital R. So the total moment of inertia, which is I, is equal to integrate from 0 to capital R all these moment of inertia values, which is 2 pi sigma into x cube dx. This is equal to 2 pi sigma into x raised to 4 by 4 from 0 to R. That is equal to 2 pi sigma into r raised to 4 by 4. Now, this is equal to 2 pi into, instead of sigma, let me write m divided by pi r square into r raised to 4 by 4. So, cancelling certain terms, we will get this is equal to m r square by 2. So that is the moment of inertia of a disk passing through an axis through the center perpendicular to the plane of the disk. That is through this axis, Z axis. Now, as case 2, let us find the moment of inertia of the same disk about an axis passing through its diameter. For that, as we have already seen, we may use the perpendicular axis theorem. Consider two axes x and y lying on the plane of this disk. So you can imagine it like this. This is the x axis and this is the y axis. Both of them lie on the plane of the disk. Z axis is perpendicular to the plane of the disk. We are asked to find out Ix and Iy. We already know the value of Iz, which is mr square by 2. Due to the symmetry of the disk, Ix and Iy are equal. Now from the perpendicular axis theorem, we have Iz is equal to Ix plus Iy. And since Ix is equal to Iy, we may write Iz is equal to 2 times Ix. We have already found out the moment of inertia of the disk about the Z axis, which is Iz. So that was mr square by 2. And since it is equal to 2 times Ix, we may write Iz is equal to 2 times Ix. That is mr square by 2 is equal to 2 times Ix, or Ix is equal to mr square by 4, which is same as Iy. So that means the moment of inertia of this disk about an axis passing through the diameter is mr square by 4. About an axis passing through the center and perpendicular to the plane of the disk is mr square by 2. And passing through the diameter, as we have obtained from the perpendicular axis theorem, it is mr square by 4. So I hope the calculation of the moment of inertia in the case of a disk is clear for you. Try to understand the concept in a more detailed manner. We have obtained the moment of inertia of the disk about an axis passing through the center and perpendicular to the plane, which is mr square by 2. And in this case, it is mr square by 4. I hope the calculations are clear for you. Thank you.